here we have a very complicated circuit, or at least more complicated than you have seen before. And we're going to use Kirchhoff's rules in order to solve for the current running in this circuit. Now, let's talk about what the circuit's doing. We've got two batteries. Here's one of my batteries, V1. Here's my other battery, V2. Okay. The longer plate here in my diagram of the battery represents the positive terminal. And then I've got 4 resistors arranged around here. We have 3 branches of the circuit here for our current to flow through. Okay, so right here we have a junction, right here we have a junction. With our junction rule, we said that all of the current coming into the junction must equal the sum of all the current coming out of the junction. I've chosen a particular direction for the current in the circuit. I'm going to call what I'm going to call I1 is the current that's running this direction down this middle branch of my circuit. Then it reaches this junction and that current divides. It splits to go through this loop here. I'm going to call this current I2, the current that's coming up around this branch. I'm going to call the current I3 the current that's coming around this branch. Okay, so I1 is this way, it has to diverge, the current diverges, it comes around, and then it has to combine back again here at junction 1 in order to go back through this way. Now I'm going to draw in 2 Kirchhoff loops. And I like to start drawing my Kirchhoff loops from an EMF source. I'm going to draw my Kirchhoff loop going, I'm going to start here at battery 2. And I'm going to start right here, and I'm going to go from the negative to the positive terminal of my battery, come through here through resistor 1, come back here from the negative to positive terminal of battery 1, come through resistor, what's that, 2, and then come back here through resistor 3. So this is loop 1, is traversing, I guess this is clockwise, around this loop here. And I'm going to call this loop 1. Okay. And then I can draw loop 2. I'm going to start loop 2 also at the EMF source here, my battery. So I'm going to draw loop 2 going from the negative to positive terminal here, coming this way, coming through R4 here, and then coming back through R3 and coming over here. Okay, this is, I'm going to call loop 2. And this one we went counterclockwise around there. So we've got 3 equations in order to get 3 unknowns. My 3 unknowns for this problem, what we're going to solve for is the current through the current I1, the current down this branch. We're going to find the current I2, and we're going to find the current I3. Okay. And in order to find those currents, the magnitude of those currents, we have to use our Kirchhoff rules. And the first rule that I always start with is the junction rule. So let's write down the equation for the junction rule for this circuit. So here's where I'm going to define my junction. And for the junction rule, the sum of all the current coming into that junction must equal the sum of all the current coming out of that junction. So here we've got current I1, and then it splits off. So I1 has to equal I2 plus I3. I'm going to call this equation 1. And then I'm going to write down the Kirchhoff's second rule, the equations for the loops as I'm going around my circuit here. So I'm going to draw or write down my equation for Kirchhoff's second rule for loop 1 and for loop 2. So Kirchhoff's second rule says that the sum of all of your potentials around the loop has to equal 0. Sum of all your potentials around the loop has to equal 0. Let's see. So if we are starting here at loop 1, we're moving through our battery from the negative to the positive terminal. So that's a positive quantity for potential. And we're gaining potential as we do that, as we move from the negative to positive terminal. So I'm going to say V2. And then as we traverse our loop, we come through resistor 1. As we move through resistor 1 in the direction of the current I2, we're decreasing our potential. So we're going to represent the potential as I times R through resistor 1. That potential is going to be minus I2 R1. V is equal to IR. The current through resistor 1 is I2. And we're decreasing our potential as we move through that resistor in the direction of current. And then we're going to come through my battery, my other battery. And we're moving through this battery from the negative to the positive terminal in the direction of the current. So we're also picking up potential. So we're going to add V1 here. And then we're going to come down here through resistor 2. So I2 is running all the way around here. So we're coming through resistor 2 in the direction of current I2. That's decreasing our potential. So we're going to say minus I2 R2. And then we've got one more element to traverse through. Around loop 1, we have to go through resistor R3. Now, as we move through R3, the current through this branch right here, we call I1. So the potential through R3, we're decreasing our potential here, and that potential is going to be minus I1 R3. And that has to equal 0. So this is our equation for loop 1 right here. Using Kirchhoff's second rule, this is our equation for loop 1. And I'm going to call that equation 2. And now we have to do our equation for loop 2 following Kirchhoff's second rule. And I've kind of run out of room here, so I'm going to do this equation right here. Okay. So for my second loop, I'm moving through my battery V2 from the negative to positive terminal in the direction of current, so I'm increasing my potential. So I'm going to have V2, positive V2, increasing my potential. I'm coming here through resistor R4. The current through R4 is what I'm calling current 3. So I'm decreasing my potential as I move through resistor 4 in the direction of current. So the potential here is going to be minus I3 R4. And then I'm going to come up here and I have to finish my loop by going back through resistor 3. And when I pass through resistor 3, I'm moving through resistor 3 in the direction of current I1. So I decrease my potential minus I1 R3. And that has to equal 0. And this is my equation that I'm going to call equation 3. I've got 3 equations, 3 unknowns. Now, what are we going to do? What's the strategy now to solve? This becomes an algebra problem. So I've got this equation, I1 is equal to I2 plus I3. In this equation here, I've got current I2 and I1. In this equation here, I've got current I1 and I3. What I'm going to do is I'm going to solve this equation for I2. That'll give me I2 in terms of I1. And I can plug it in here. I'm going to solve this equation right here for I3. That's going to give me I3 in terms of I1. And I can put that in here. And then that will leave me with this equation only being in term of, only have unknown of I1. And then I can get I1, and then I can plug it into all these other pieces here. Okay, so let's solve this equation right here for the current I2. Now this is a little bit different than what I ask you to usually do. We're going to solve this equation I2, and when we do it, we're just going to put in the numerical values, and we're not going to include the units. Okay, that's pretty unusual for what I do. But we get too many of these variables hanging around and it gets a little bit confusing. So we're just going to plug in the numbers. V2 is 14 volts minus, we've got I2 R1. So R1 is 4 ohms, so minus 4 I2 plus V1, which is 11 volts, minus I2 R2. R2 is also 4 ohms, so whoops, minus 4 I2 again. And then we've got minus I1 R3. R3 is 8, so minus 8 I1. That equals 0. Okay, so I took this equation and I just put in all the numerical values that we know here. Okay, so I can put like terms together. 14 plus 11 is 25, so that's 25. Minus 4 I2 plus minus 4 I2, that's minus 8 I2, and then minus 8 I1 equals 0. And we want to solve this for I2. So I'm going to take 8 I2 and move it to one side of the equation. So I'm going to have 8 I2 is equal to 25 minus 8 I1. I divide both sides by 8. So I divide each one of these individual terms by 8. So I2 equals 25 divided by 8, which is 3.125 minus 8 over 8, which is 1. So minus 1 I1. So now I have this new equation, equation 3, which gives me I2 in terms of I1. Okay, so I'm going to leave it right here for now. Now I'm going to come over here to this equation right here. This was equation 3 that we got from doing Kirchhoff's second rule around loop 2. So then we have 14, that's V2, minus I3 R4. Resistor 4 is 2 ohms, so minus 2 I3, minus I1 R3. R3 is 8 ohms, so minus 8 I1, and that equals 0. And we're going to solve this equation for I3. Okay, so I'm going to add 2 I3 to the other side. So then I have 2 I3 is equal to 14 minus 8 I1. Divide both sides by 2. So divide each of these terms by 2. I3 is equal to 14 over 2, that's 7, minus 8 over 2, that's 4 I1. And I'm going to call that equation 5. Okay, so now I've got, I'm going to put a box here, or maybe just underline. I1 is equal to I2 plus I3. I took loop 1 and I solved it to find I2 in terms of I1. I took loop 2 and I solved it for I3 in terms of I1. And now what I can do is I can plug in this equation in here for I2, and I can plug in this equation in here for I3. So since I'm running out of room here, we're gonna do this down here. Okay, I1 is equal to I2. I2 was 3.125 minus 1 I1. Okay, plus I3. I3 was 7 minus 4 I1. Okay, cool. So now the only variables that I have in this problem are I1. And now I have to combine all the terms together that have I1. So on this side of the equation, I have got I1 equals 3.125 plus 7. And that gives me 10.125. I have minus 1 I1 plus minus 4I1. So that's minus 5I1. Okay. Now I add 5 to this side. Add 5 to both sides. Plus 5I1. So now I have 6I1 is equal to 10.125. Okay. Now if I divide both sides by 6, I find that I1 is equal to 10.125 divided by 6. So I1 is equal to 1.6875 amperes. Okay, so now we got one of those currents. Okay, so since we got one of these currents, we got I1. So all of these other equations that we did over here and over here, we solved for I2 and I3 in terms of I1. So we just plug in the quantity that we got for I1 into both of those equations, and then we get what I2 and I3 should be. So if we do this for I2 here, we've got 3.125 minus 1 times 1.6875. And that tells me that I2 is equal to 1.4375 amperes. Okay? And then for I3 is equal to 7 minus 4 times 1.6875 amperes. And so I3 is equal to 0.25 amperes. That's I3. Okay, so, and this was I2. So now we've got the current I1, the current I2, the current I3. And we saw earlier that I1 has to equal I2 plus I3. So if I add I2 and I3 together, I will get back my current here, I1. Now this is the only way that we can solve these problems, is by applying the junction rule and by drawing in our Kirchhoff loops here and applying Kirchhoff's second rule, the sum of the potential around that loop equals 0. We get 3 equations, 3 unknowns. We've got to solve them algebraically in order to get our unknowns, our current. That's a lot of work to get to the answer. The good news is that your pre-lab question here, you follow this exact same procedure. The circuit is set up in the exact same way. You're going to get similar equations, the exact same equations here. The only thing that's different is going to be your numerical values for the potentials and for the resistances. And so you'll use those in your equations in order to get the current I1, I2, and I3. Now, in your at-home lab, I'm going to give you a new circuit. It's going to look a little bit different from this, but it's going to have 2 batteries and multiple resistors. What you have to do is set up your own equations for the junction rule and put in 2 loops and set up your own equations for Kirchhoff's second rule around both of the loops in your circuit. Those equations are going to look different from the ones here because that circuit's going to be different. And what I'm going to ask you to do, you're going to set up your equations. I'm not going to ask you to solve for the current. I'm going to ask you to take measurements of the potential across each of the resistors and the current in your circuit. You will use those measurements and plug them into your equation for the junction rule, your equation for loop 1, and your equation for loop 2. And hopefully when you plug in those values you measured into those equations, you find that they are true. You find that I1 measured is equal to I2 plus I3 measured. You find that the sum of all of your potentials around loop 1 will equal 0. You'll find the sum of all of your potentials around loop 2 will equal 0. So you're going to have to set up your Kirchhoff loop equations. I'm not going to ask you to solve in the lab participation for the currents. You're going to take those measurements And you're going to use those measurements in order to verify that the equations you came up with for Kirchhoff's first and second rules are correct for your circuit.